Hello friends, today we are going to discuss about green chemistry. Green chemistry, which is also called sustainable chemistry, is an area of chemistry and chemical engineering focused on the designing of products and processes that minimize or eliminate the use and generation of hazardous substances. Green chemistry discusses the engineering concept of pollution prevention and zero waste both at laboratory and industry scales. It encourages the use of economical techniques that not only improve the yield but also bring down the cost of disposal of wastes at the end of a chemical process. There are so many benefits of chemical industry. They are used to make so many products like antibiotics and other medicines, fertilizers, pesticides, plastics, nylon, rayon, polyester, and all the synthetic materials, gasoline and fuels, and also it is used in the water purification techniques. But the reverse effect of chemicals are also reported. The known example is the Cuyahoga River in Ohio becomes so polluted with chemicals that it caught in fire. Second example is a plant accident in Bhopal, which is in India, released methyl isocyanate, which caused nearly 4,000 people died. So that we need a green chemistry to save our environment. So what is green chemistry? Green chemistry is defined as environmentally beginning chemical synthesis. It focuses on a process that reduces a use and generation of hazardous substances or byproducts. The one known example of green chemistry is in dry cleaning. Liquid carbon dioxide can be used as a safer solvent if a wetting agent is used with it to dissolve grease. This method is now being used commercially by some dry cleaners. The chemicals used for dry cleaning are perc, which is known as perchloroethylene, is the solvent most widely used in dry cleaning of clothing. Perc is suspected of causing cancer and its disposal can contaminate groundwater. So, friends, now we will see the principles of green chemistry. There are 12 principles of green chemistry. In that, first one is it is better to prevent waste than to treat or clean up waste after it is formed. To know that, we can see one example. Carry out a synthesis by the method which involves the minimum waste, means no byproducts. The cost of treatment and disposal of waste adds to the overall cost of the production. The waste, if discharged in atmosphere, sea and land, causes pollution and require expenditure for cleaning. The second principle is the synthetic material should be designed to maximize the incorporation of all materials used in the process into the final product. With a 100% yield, such synthesis may generate significant amount of waste or byproducts. Such a synthesis, even though it is 100%, is not considered to be a green synthesis. Now, we know that atom economy. So, what is atom economy and in which reactions it is formed? We know the four reactions: the rearrangement reaction, addition reaction, substitution reaction, elimination reaction. In all these four reactions, the rearrangement and addition reaction is known as the atom economy. Now, third principle is wherever practicable, synthetic methodologies should be designed to use and generate substances that possess little or no toxicity to human health and the environment. The fourth principle is the chemical products should be designed to preserve efficiency of function while reducing toxicity. In that, the chemical synthesized, for example, we are synthesizing dyes, paints, cosmetics, pharmaceuticals, etc., should be safe to use. The fifth principle is the use of auxiliary substances, which are solvents, separation agents, etc., should be made unnecessary. In that, a number of solvents like chloroform, benzene, carbon tetrachloride, etc. have been used due to their excellent solvent properties. However, the halogenated solvents have been identified as human carcinogens. Also, benzene and other aromatic hydrocarbons are believed to promote cancer in humans and animals. CFC, which have been widely used as cleaning agents in refrigerator, are responsible for depleting the ozone layer. Now, sixth principle is energy requirement should be recognized for their environmental and economic impacts and should be minimized. The use of catalyst has the great advantage of lowering the requirement of energy of a reaction. In case the final product is not pure, it has to be purified by distillation, recrystallization or ultrafiltration. All these steps require energy. So the process should be designed in such a way that there is no need for separation or purification. The seventh principle is raw material or feedstock should be renewable rather than depleting, whenever technically and economically practicable. The starting materials can be obtained from renewable or non-renewable materials. For example, petrochemicals are mostly obtained from petroleum oil, which is non-renewable source, since its formation take millions of years. The starting material, which can be obtained from agriculture or biological processes, are renewable materials. For example, carbon dioxide and methane gas. Now, eighth principle is unnecessary derivatization, which is blocking group, protection, deprotection group, temporarily modification of physical or chemical processes should be avoided whenever possible. We have to avoid some derivatization which cause pollution. Now, the ninth principle is catalytic reagents, as selective as possible, are superior to stoichiometric reagents. In that, in some reactions, if one of the starting material A or B is a limiting reagent, in such cases, even if the yield is 100%, some unreacted starting material will be left over as waste. In other cases, if the reagents A and B do not give 100% yield of the product C, both the excess of unreacted reagents will form part of waste. By using catalyst, both starting material utilization is enhanced and formation of waste reduced. The 10th principle is the chemical products should be so designed that at the end of their function, they do not persist in the environment and break down into innocuous degradation products. It is important that the products that are synthesized should be biodegradable. The non-biodegradable chemicals remain in the same form in the environment or are taken by various plants and animals, for example, pesticides and plastics. The 11th principle is analytical methodologies needs to be further developed to allow for real-time in-process monitoring and control prior to the formation of hazardous substances. Analytical methodologies and technology have been developed which allow the prevention and minimization of the generation of hazardous substances in chemical process. One need to have accurate and reliable sensors, monitors to assess the hazardous in process. These procedures can prevent any accident which may occur in chemical plants. The 12th and last principle is substances and the forms of a substance used in a chemical process should be chosen so as to minimize the potential for chemical accidents, including releases, explosions, and fires. The occurrence of accidents in chemical industry must be avoided The accidents in Bhopal and many others have resulted in the loss of thousands of lives. Now, green chemistry is about reducing the waste, reducing materials, reducing hazards, reducing energy and risk, and the most important, environmental impact, and also the cost. So now we will see some green chemistry solvents which are used and which do not have environmental pollution. The first one is ionic liquids. The ionic liquids are ionic compounds that have a melting point below 100 degrees centigrade. Many of them are even in liquid at room temperature. They consist entirely of ionic species. They have many fascinating properties which make them the fundamental interest to all chemists, since both the thermodynamic and kinetic of reaction carried out in ionic liquids are different to those in conventional solvents. These are some of the examples of ionic liquids. The properties of ionic liquids are they have no effective vapor pressure. They have high density and electrical conductivity. They are good solvents for many inorganic and organic materials. Liquid range of 300 degrees centigrade, allowing tremendous kinetic control. They possess high thermal stability. Their water sensitivity does not affect their industrial application. They are immiscible with number of organic solvents and provide non-aqueous polar alternatives for two-phase systems. The applications of ionic liquids are they offer green solvent in polar reaction. They are absorbents of acidic gases such as carbon dioxide, sulfur dioxide and hydrogen sulfide. They offer suitable media in liquid-liquid separation processes of aromatic and organosulfurs from hydrocarbons. They are catalysts in petrochemical processes such as hydrogenation of olefins. The electrolyte for batteries, fuel cell and dye-sensitized solar cells are also used ionic liquids. The second example of green solvent is water. The water is the best ionic solvent. Now, third is supercritical solvents. They are the materials which can generally exist in three states: solid, liquid and gas. A change from one state to other occurs if pressure or temperature is changed sufficiently. A supercritical fluid is a material which can be either liquid or gas used in a state above the critical temperature and critical pressure, where gases and liquids can coexist. It shows unique properties that are different from those of either gases or liquids under standard conditions. Two supercritical fluids are of particular interest, which are carbon dioxide and water. The carbon dioxide has a low critical temperature of 304 Kelvin and a moderate critical pressure of 73 bar. It is non-flammable, non-toxic and environmentally friendly. It is often used to replace toxins, freons and certain organic solvents. Further, it is miscible with a variety of organic solvents and is readily recovered after processing. It is also a small and linear molecule and thus diffuses faster than conventional liquid solvents. The second, water has a critical temperature of 647 Kelvin and a critical pressure of 220 bar due to its high polarity. The character of water at supercritical conditions changes from one that supports only ionic species at ambient conditions to one that dissolves paraffin, aromatics, gases and salts. Due to its unique property, research has been carried out on supercritical water for reaction and separation processes to treat toxic wastewater. Supercritical fluids such as water and carbon dioxide are substances that are compatible with the Earth's environment. The carbon dioxide has the advantage over other supercritical fluids that its critical temperature is remarkably low at only 31.1 degrees centigrade. So high temperature are not necessary with the carbon dioxide. The applications of supercritical fluids are the advantages of supercritical fluid extraction are that is relatively rapid because of the low viscosities and high diffusivities associated with supercritical fluids. The carbon dioxide is most common supercritical solvent. It is used on large scale for the decaffeination of green coffee beans, the extraction of hops for beer production, and the production of essential oils and pharmaceutical products from plants. Few laboratory test methods include the use of supercritical fluid extraction as an extraction method instead of using traditional solvents. Uses supercritical carbon dioxide instead of perc or other undesirable solvents for dry cleaning. The detergents which are soluble in carbon dioxide improve the solvating power of solvents. Changing the conditions of the reaction solvent can allow separation of phases for product removal or single phase for reaction. The rapid diffusion accelerates diffusion controlled reaction. Thank you.